I forgot to record last one. Okay, so today we're going to dive right into rotation. FYI, rotation is going to be about 9-10 classes, but that's going to include 2 exams. So it's basically spend 4 days, do as much as we can in this packet, and then we'll exam. And then another packet will come out to involve rotational energy and momentum. And yeah, we're going to say those words again, but for rotating objects. What we're doing now for the next 4 classes, or 5, depending, I can't remember exactly when April 5th occurs, but we'll be looking at the kinematics and forces of rotating objects, all right? So in a way, you're going to get a review of kinematics and forces, but with the twist. Well, for rotating objects, so, you know, twisting, rotation, a little bit of what I can get there. Okay. And so page 1, we're basically, I'm not going to sit here and, you know, define things that we've already done, but we're going to take a comparison look at the old kinematics and the new kinematics, at the old forces and the new forces. But before I do that, just want to say, before spring break, I had sent out a couple videos. Hey, here's rotation. Here's a foldable that if you want to build it, if you want to fill it in, you can. Do y'all know what a foldable is? Is that still a thing? I know it's still trending. Okay, that's great. It may or may not be at many high school classes, but foldables, you know, you can fold something in half. You got the trifold. This one is just super duper awesome. If you love foldables, and I have directions on how to make it in terms of building it, because we got 2 colors here. That's not colored in. That's 2 different pieces of paper. It's like basket weaving, right? So it's called an accordion fold. And if you want to go back to that video, or I can post it in the current module, this is just a study tool. It's not something that you can use on any test or exam, but it's just a study tool. So if you're okay with just notes, then we're going to put the same information here. But the foldable, what's unique about this accordion fold and basket weaving, you got to watch this. You ready? Ready? Watching? Boom, 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 boom. What? It's got a secret panel. But wait, there's more. If you reverse the accordion fold and go the other direction, you get another secret panel. So not necessarily for physics. Okay, you don't have to fill in every single spot, but you know, if you ever want to test yourself on material that might have more information than what you want to write, you could put, I know. So it's just an awesome foldable accordion fold with secret panel. So there's a video on how to build it, and then a physics video, you know, how to fill it in. And it's mainly left side kinematics old, right side kinematics new for rotating objects. All right. So I have the cardstock, I have the dimensions. If you want, you can do this, but we're not going to use class time to do it. All right. Yes, yes. Okay. So hopefully you've copied over the OneNote content library tab for rotation, or you have your notes packet there. Let's go in and jot down. So this is packet 1. For the exam 1, note to self, our exam for rotation number 1 is April 5th. And if you're like, oh gosh, that's so long, or that's so far away, it's like 4 or 5 classes. I can't remember exactly, but it's just 4 or 5 classes. So this packet is 30 pages. Y'all know the drill. We're not going to fill all these out, right? The last chunk is NIMSY. We've got a couple pages on rotational kinematics, lots of pages with torque, and then some other applications like pulleys and rolling. And so to get this started, let's go back to the basics. So I'm basically going to think 2 columns here, okay? Left side, old. New side, right side, new. Sorry, I said that starting backwards. And so let's go back to the beginning. August, we started talking about position, time, Speed velocity. What was one of our fundamental defining equations? Well, even before forces. Yes, that's fundamental to the grand scheme of things, forces. But in terms of kinematics, you got an object box sliding on a ramp, right? Maybe it has well, I guess if it's a ramp, it would have constant acceleration. But if it was on a frictionless surface, maybe it's got a constant velocity, right? And so y'all remember speed velocity is some distance displacement divided by time, right? A time interval. Unit, meters per second. Yes?
Yes.
Now, this is the equation you can use if there's a constant velocity or instantaneous, like a short window of time. But what if you don't have constant velocity? What if it's changing? How do we define a change in velocity? We get acceleration. Units, meters per second squared. Pretty boring, right? And then through a couple of, tricks or substitutions of many different equations, we got our three constant acceleration equations that do appear as the top left on the formula chart. And so just to remind you, VF equals VI plus AT, XF equals XI. And by the way, we could put those in terms of delta X, which was actually my norm, and then again, more derivation, we got the third equation, VF squared equals VI squared plus 2A, and then a change in your linear position. And so those were good for constant acceleration, right? Those three are called the constant acceleration equations for objects moving in a linear fashion, linear straight line, right? Now, yeah, we broke it up with projectiles, okay, one dimension at a time. We considered them independent of each other, and we blended them, any of these, with maybe a force application, yes? And so maybe you have constant velocity or constant acceleration. Well, let's go to the right-hand side. Think kind of double column here. What if I have an object moving in a circle? Now, first of all, we need to clarify. In December, we did circular motion. I swung a ball on a string. We looked at driving a car around either a roller coaster or maybe just on a flat surface, right? And so if I walk in a circle, I'm tracing, my feet are tracing a circle, right? That is not rotation, it's just exclusive circular motion. So what are we going to do now? Well, now, what if I stand in the center of that circle and I rotate? Okay? So a little bit different, still circular motion talking about. Now, older people, we get dizzy. So bear with me. I'm not going to spin long, so you got to watch. I do have a frictionless platform, or it's as close to frictionless as we can get. And I would say you can come up and try this, but please be careful because just a little tap and it moves, okay? And so maybe you see the platform, maybe you don't. But I'm going to stand in the center, holding something stationary for safety, right? And so I'm just standing here. But if I push off, I can spin, right? And spin a little bit more. What if I put my arms out? I'll slow down. Why do figure skaters bring their arms in? Oh, I need to stop.
Be safe.
What? No. It speeds them up. They can make the rotation in a shorter amount of time. It later will say they're decreasing their inertia, right? And conservation of angular momentum is in our future. So that's kind of a fast forwarding, but it shows you a difference of rather than walking in a circle, you're literally spinning, okay, about an axis. And so take maybe one fingertip, take one shoulder, follow it along in the circular path. Does it travel a linear displacement? No. Does it have linear velocity or speed? Technically, yes, but you don't see it as well. Tangent velocity. Okay. But we're going to rewrite these same equations, but with angular terms. Now, there's a lot of Greek symbols coming your way. We've introduced theta, delta, omega already. There's more coming, but here's the good news. On the AP formula chart, all the Greek letters are there at the bottom of the key, bottom of the legend. Okay, so you don't have to know which Greek letter. What's tau? You don't have to know that. You don't have to know omega. You just have to recognize that symbol and then know what it represents, okay? And so instead of linear velocity, we have angular velocity. How might we define, we've kind of already done this, angular velocity? It's not a change in linear position, it's a change in angular position. And so if you traced one shoulder, whenever I'm turning in a circle, look at one revolution. If my shoulder traces a circle, it makes how much of a angular displacement? 2 pi radians, okay? So watch. We'll say delta theta. We're not talking about, I know we're in degree mode for our calculator, but we usually don't describe the angular displacement in terms of degrees. You could, but usually it's in radians. And then time. Do you think time cares if we move in a circle or straight line? No, just like time didn't care in projectiles if we were moving vertically, horizontally, or both. Time is time. And so we'll keep time right there. Now, we may not have written it this way, but we applied it this way. What's the unit for angular velocity? Not meters per second. Say again. I can't hear you. Oh, so you could say degrees per second, but the norm is radians per second. I know it's weird. We're in degree mode, but you're talking about radians, okay? We're using radians. Is that part of the circle? Is it a full circle? 2 pi radian? Is it half a circle? 1 pi? But radians per second is our unit for angular velocity. Now, this is the equation you would use if something was rotating at a constant rate, a constant angular velocity. But more than likely, I mean, the platform that I once was spinning on has now come to a stop. And so if things change their angular velocity, then what's happening here? The object must be, what's a change in velocity? Acceleration. Just put the word angular in front of it. And so the next one we're going to have is angular acceleration. Now, Greek, lowercase a is already taken, capital A is already taken, and the spirit of Greek letters for the rotational quantities, we've got alpha. Alpha. Looks like a fish. Someone was eating goldfish during the exam. Looks like a goldfish, right? So angular acceleration isn't going to be a delta V over T. It's going to be equal to a change in omega over T. It's the rate at which your angular velocity changes. Unit. What would the unit for our angular acceleration be? Correct, radians per second squared. Are you noticing the comparison to linear? Okay, and so in a way, this is review of linear motion, but we're taking it to rotating objects. What about the constant acceleration equations? For linear moving objects, there's the 3. What if I have constant angular acceleration? What would these three turn into? And warning, AP gives you all three linear equations, but they only give you two rotational. So if you learn how to translate to rotation with Greek symbols, then you'll easily be able to get the third equation. And so what about the first one? Final linear velocity turns into final angular velocity equals initial angular velocity plus angular acceleration times time. Now, you don't have to be a professional Greek writer. Just do your best so that the grader knows what you're trying to say. What about the next equation? Instead of a linear position, we want an angular position. And so this is that theta final equals theta initial. And by the way, you can subtract initial and put it in terms of angular displacement plus omega it plus 1/2 alpha t squared. Same but different. Now those two are on your formula chart, okay? The first two are not because they are defining equations, but these two are. Locate them now. Where are these two equations on our formula chart? Say again. Yeah, so it's middle of the first column if you look in that region. Just find the Greek symbols, right? Now you're doing rotational stuff. But that third one is not there. So let's learn how to make that third equation. Well, it'd be omega f, don't forget to square it, equals omega I, don't forget to square it, plus 2 times alpha times final theta, angular position, minus initial angular position. And again, we can put either of those, linear or angular, as delta theta. And I'm only showing you that because it's actually very common to just say delta x, delta x. Maybe the problem doesn't need your exact position. Maybe they just solve for the displacement, angular displacement. Good on those? And all the kinematic graphs that we had, okay, position, velocity, time, acceleration graphs. Remember, to go down to the next level, you had to do what strategy? Derivative or slope, right? The slope of position time graph gives you velocity. The slope of velocity gives you acceleration. And so you can use slope to go to the next level. Well, the same thing's true with our angular quantities, except your y-axis would have different labels. And so slope will bring you to the next level. So I don't have a data line there, but it's just the concept. You can still apply the kinematic graphical strategies to your angular terms. Good deal? So here in a second, we will do some rotational kinematics practice, okay? I want to introduce, what did we do after kinematics? Oh, we did, that's still part of kinematics, yeah, 1D, 2D. Forces, we did forces. So what was the big idea in forces? We had Newton's laws, right? Newton's first law. Objects rotating at a certain angular velocity will continue to rotate at that same angular velocity unless you act upon by an outside force, right? That was me pushing off from some source. So you can still apply Newton's first law, Newton's third law. Now Newton's second law has an equation. What's our equation for Newton's second law? Right, F net equals ma. Or on the formula chart, just a reminder, they solve it for acceleration. F net divided by mass This is for objects in linear motion. Now, yeah, projectiles, again, we treat the X and Y independent. What about rotating objects? Is it just the force that accelerates them? It turns out here's where it gets a little different, okay? Have you ever heard the word torque?
Yes.
What is torque? Generally speaking, it's the force needed by whatever means, motor or my hand pushing off on the computer card, to cause an object to rotate, to cause angular acceleration. And so we actually get Newton's second law for rotating objects. Net torque, here's a new Greek symbol, kind of like a, I don't know, a swirly T. You can check on the formula chart how it's officially written, but there's my net torque, equals, now it's not M alpha. I know that you may be thinking, oh, M alpha, mass doesn't have anything angular about it. It turns out, here's where it gets a little tricky. Yes, mass is important, but how the mass is distributed in the object is really important. And so here's a new term, a new variable, not Greek, a capital I. What does the formula chart say the capital I is? Rotational inertia. Now later, if you see on the screen, we'll spend some pages there just devoted to inertia. So we're not going to hit that part hard here in the beginning. Well, horsepower is really an energy relationship and power. I think 1 horsepower is 760 watts. Okay, sure. You'll Google it later. But I think horsepower is how much power the motor can distribute to whatever object it's trying to move. So yes, motors have things spinning. There is rotation involved, but just horsepower in general. Okay, so there's our mass comparison. But again, it's not exactly mass. We don't have a rotational mass, but it gets into how the mass is distributed. And then times alpha. Now this one is on the formula chart, but I believe it's solved for alpha. Very similar to Newton's second law. Alpha, angular acceleration, would equal your net torque divided by that rotational inertia. It's also called moment of inertia. If you read a review book or watch a review video or, use another resource, it has a couple names. Again, spirit of inertia. And so torque, I said it's going to be a little bit different than force. It involves force, but it takes it further. And so I'll give you the equation, and then I'm going to go open a door. Torque requires a force. Think about what I had to do here to make myself rotate on the rotating platform. Someone had to push me, or I pushed off a stationary object, right? So I pushed at just the right moment. Now, we may not think about this nitty-gritty in everyday life. Remember, walking, you can really analyze walking nitty-gritty with physics, but every day we just walk. We don't think about gripping friction in Newton's third law, right? So it's more than the force, how far away the force is from the axis of rotation. Okay? And so now, bear with me, I'll take that equation a little further here in a second, but look at, I'm going to try and open a door, okay? Just a cabinet door right over here. So you've opened cabinets before, and you could do the same on the classroom door. How do we open doors?
Pull
Pull. We exert a force. Where?
on the handle.
On the handle. Where's the handle?
On the door.
Where on the door?
Anywhere?
No.
Usually on the end of it.
Usually on one end, and focus on this one cabinet door, okay? I'm not going to go through and open all of them. So just one door right here. Here's the handle on the left side of that door. Why the left side? Why not put it over here? From the hinge. And so here we have a hinge. I know it's covered up with a piece of paper, but here we have a hinge. What's the hinge? It's a fixed point. This side of the door is not going to rotate, right? This point here at the hinge is not really going to move if the hinge is doing its job, right? It's not going to move in a line. It's not going to move in a circle. And so good physics is to put the hinge on the opposite end of that door. But true story, couldn't we put it anywhere?
Yeah.
Now, I'm not going vertical here, okay, because we want to open it horizontally. But you could put the handle anywhere. Ignore the glass. Imagine it's solid wood. You could put it anywhere. In fact, I've lived in a house where the handle was in the middle of the door, vertically and horizontally. It looked good.
It's so inefficient.
But it's inefficient, okay?
Because then you hit your own knuckle.
And as a short person, I didn't appreciate it. So most days I just went to the corner of the cabinet and pulled, right? And so you could put the handle anywhere, no offense if you live in a house with the handle in the middle of the door. It looks nice, mind you, okay? But the most efficient place to put it, and why do we talk about efficient? Well, if we were to come in here, and you can try this when you open a door, like the classroom door, go home and try it. You can try and open the door at the very end. That wasn't too bad. And these have some kind of like self-closing latch that I'm fighting against. Can I open it at the middle of the door?
Oh, yeah.
How am I going to have to pull? Out in both cases, but compared to the force over here at the very end where I have more distance, this is easier than the middle, okay? Try it on your bedroom door tonight. Open the door, push it different places, okay? And so one more piece to that. I wrote R perp. R perp a lot of times is called the lever arm. Have you heard leverage? You need more leverage, okay? And so what's the lever arm? Here we go. It's the distance from your axis of rotation, AKA a hinge, to where the force is exerted. And so R perp is the distance from axis of rotation. That's like the center of the circle it makes, to where your force is. Now I'm going to get fancy and call that last piece a little bit something different. It's the distance from the axis of rotation to the line of action. And I'm in parentheses, I'm going to say force. Line of force, line of action. Later when we get to angular momentum, you'll hear me say line of action, okay? But it's similar to where the force is exerted. Now, why the perpendicular? Well, let me stay here at the cabinet. Let me take this horizontal door that you see. Just focus on the bottom of the door. Horizontal, yes? Can I push horizontally to open the door? Not even hypothetically. If I push in the same direction that the lever arm is oriented, I have no torque. Same thing if I pull straight to the right, and I'm really pulling. Now, if the hinge is weak, I might take the whole door off the hinge, right? But as long as the hinge is holding it in place, am I going to open the door pulling horizontal if the lever arm is horizontal? But could I maybe angle that force and open? And the best, most efficient place to pull is when my lever arm and my force, my line of action, are literally perpendicular to each other. And so you get maximum when it's straight 90 degrees. If it's not 90 degrees, if my arm makes some kind of non-90 angle with the door, then I got to take a look at components, okay? And so you'll see on the formula chart, they give you this equation. I think they say R first and then F, but then they also give you FR sine theta, okay? So if they're not 90, some angle below, you got to do the sine theta of one of them. True story. You can either do the component of the force, which is what I'd probably do in that opening of the door example. Or if it's, a different example, maybe you're like, ooh, I want to do the perpendicular lever arm, okay, R perp. And you can do that. Overall, you'll see a lot of examples. I do it both ways. And really, it's just whatever I see first, okay? When you draw it out, force diagrams, we're going to change the way we draw force diagrams this unit, okay? Not today, but next time we'll start drawing our force diagrams differently. And so all this is coming, but do you get the general torque? One more thing before we do some practice, let me show you. Do y'all know what a merry-go-round is? Okay. So when I say merry-go-round, in my mind, there are not horses on it. True story. Is it a rotating platform? Yeah, a carousel, merry-go-round. At the end of the day, it's the same physics, okay, except the horses may go up and down as you make your circle. But this, the red and yellow, that's the merry-go-round that I think of. I know that now they have seats on them, and that's actually to be safer. Where's the safest spot on this merry-go-round? In the middle, okay? If you get motion sickness very easily, I would sit in the middle, okay? Because if you sit on the end, you're further from the axis of rotation. You're going to have a bigger lever arm, right? You're going to have more angular acceleration the further out you go. Does that make sense? And then the other thing, a lot of you are driving, flat tires happen. Do you know how to change a flat tire?
Yes.
YouTube it before you move to another state, from help. AAA is real, but jacks, car jacks. Okay, now there's a couple varieties. The one with like that triangular shape, I think is one that might come with vehicles. No?
It does.
It does. Yeah, to me, I want to talk about the one I have bigger, right? The good one. And so this one, that black disc that you see on the left-hand side, not the wheel, but above, that's going to go on the axle, yeah, it's where you put it. It's just lift up the car. You don't want to put it on a movable piece of the car. You want to put it on the axle, the part that doesn't move on the car. And so you put it there. Now the rod going out on the right side, that's your lever arm, right? And so you have to push down for the car to go up, and that's a pretty small lever arm. The one I grew up with, my dad gave me an extender. I don't know if they all come with this, but you took the handle part off, you put another extender, so it kind of doubled your lever arm, okay? Why does it make it easier? My force, maybe I've maximized my force, but when you raise the lever, increase the lever arm, now my force is being used more efficiently, and you can lift the car up with the jack, maybe in 2 or 3 pumps rather than, 8 or 10. Yeah? Okay. So that's a car jack, YouTube. I'm sure there's 100 YouTube videos on how to change a flat tire. But to me, that's a good life skill to have before you move to another state or before you move away to college, right? Okay. So 1 second and we'll move on to page 2. Resume. Okay. So torque, we'll mainly start talking about next class. Today, what I want to do is do some kinematics. Good review of kinematics, but with a twist, with some rotational terms. So page 2 and 3 are pretty much, maybe it's blended through a couple other problems, but in terms of being exclusive to rotational kinematics, pages 2 and 3. So maybe we're lucky, and no, we're not going to be lucky really at all. We might just get one done, two done before the bell. And so it says, number one, I'm going to dive right in. A record. Do y'all know what a record is? Pre-CD. It rotates. It's a rotating disc, but instead of a laser reading it, you have this little needle, okay? So it's on a turntable similar to our merry-go-round, similar to that rotating disc that I stood on. It starts out initially at rest. Now, in the past, we said VI equals 0. Well, that can still be true, but in terms of angular quantities, what equals 0 now? Not equilibrium. What equals 0 when you start at rest? Okay, so your initial angular position, we're basically saying wherever, if maybe we take this record player, we put a little paint on one dot of the record. And so that dot is going to start at rest. Now, it also tells us something else. What kind of velocity? Angular velocity is also 0 initially. Okay, so omega I equals 0. When the table is turned on, the record uniformly, aka constantly, we made a big deal about it back in linear kinematics, still true. It uniformly accelerates, constant acceleration, to a max speed of 60 revolutions per second. Did we say the SI unit for angular velocity was revolutions per second? It should be radians per second after only half a second. So part A says, what is the final velocity? Omega. And so they tell us 60 revolutions per second. Y'all, it's just a conversion from revolutions, aka a circle, to radians. And so one revolution is how many radians? 2 pi. Revolutions cancels out. And for quickness, I'm going to leave it in terms of pi. So 120 pi radians per second. Yes?
Yes.
Now that's at half a second. Okay? Because they told us at that point, only half a second had passed. Now this is omega F. Remember, omega I was 0. Is this going to turn at a constant angular velocity? No, it said it constantly accelerates. What is the record's angular acceleration? So the defining equation, alpha equals a change in omega over a change in t. So final minus initial in both cases. And so final angular velocity minus initial angular velocity divided by the time. Are we all okay with initial time being 0?
Yeah.
Okay, so delta t is t final is just t, time elapsed. And initial angular velocity zeroes out. And so we've got this 120 pi radians per second divided by half a second.
No.
And so leave pi alone. We'll keep all these answers in terms of pi. What's 120 divided by half? 240 pi radians per second squared. All right, we'll finish this up next class. Only about 30 minutes max on rotational kinematics, and we'll be moving on to torque, okay?